All right, time for another draftphysics.com, debatephysics.com also. But still can't find anyone willing to make counter arguments to the arguments I make, reasoned counter arguments. So I have found another doctor, Dr. John, okay, to ask physics questions to and see if they'll answer them, kind of honestly and with some sort of credible, information or counter arguments. So I'll ask him, does he really think it takes 100 times the energy to spin a motor 10 times faster? I guess it's 90 times. You're using 10. That somehow you need 90 times the energy to spin it from 10 rotations per second to 100 rotations per second takes 100 times the fuel. I should just do 1 rotation per second to 10 rotations per second. Somehow takes 90 times the fuel. Not 9 times the fuel, 90 times. Simple answer, but, probably won't. Okay, and if he does, he'll answer that, well, no, of course that doesn't happen because, the relativity or something. But, yeah, that won't be a deep, thoughtful answer. But anyway, so here's his website. So he's done a couple of videos of some interest in terms of relevance to kinetics, okay, kinematic equations as they call it. And such, but nothing really delving into any of the real arguments. I mean, some talk about scalars and vectors, and of course that doesn't make any sense to me. So maybe I'll just play some of that, and that'll give me a jumping ground to introduce the counter argument, which is, first off, you're not teaching Newton's physics, you're teaching Leibnizian physics. You're Leibnizians, you're not Newtonian. And frankly, at least 2 out of 3 of Newton's laws are completely destroyed by the kinetic energy theory. I mean, you really can't claim that, Newton overtly said twice the force, twice the speed, 3 times the force, 3 times the motion. No squared functions. Okay, clearly not a Leibnizian. And then the third law, what sense does it make to say equal and opposite reactions when, the bullet has 2,000 joules and the gun recoil has 2 joules? Where's the equal and opposite reaction? There's no equal and opposite. It's completely unequal and unopposite. So, lots of examples. So, I'll go find the appropriate place in the first video. And then I'll play some of the second video, and through all of that I should be able to get to I'll get to some percentage of the countless arguments that can be made illustrating how you have no evidence for this theory, that it's, and it doesn't make any sense. It creates preposterous paradoxes like the bullet and the gun. Alright, so here's the first video he made a few months ago, 7 months ago, something like that, 9 months ago. Alright, just going over units, and then he's going to use F equals ma as an example. And so just brings up the opportunity to say that's not Newton's mechanics. You shouldn't slander Newton with it because Newton didn't say it. And it's Leibnizian mechanics because you think acceleration is per second, even when it's not per second, even when it's only 3 seconds or 7 seconds. You think it should be a squared number of seconds. It's not a squared number of seconds. It's a specific number of seconds. You can add 60 miles an hour. That's it, 1 unit of 60 miles an hour. Or you can add it every hour. You could add it for 3 hours. You could add it for 10 hours. There's no squared hours.
Symbols. An example helps highlight this point. Consider Newton's second law, where the net force acting on an object is equal to...
So it's not Newton's second law. So Newton's second law is what I just said before, which is twice the force, twice the velocity, 3 times the force, 3 times the velocity. Acceleration is just a change in velocity. It's just adding a velocity. So if you're going 60 miles an hour and you accelerate 60 miles an hour, then you're going 120 miles an hour. You just add them. There is no per second per second. You don't say, I increased my speed 60 miles an hour per hour. Nobody says that, and we certainly wouldn't notate it per hour. Certainly shouldn't be notated as hours squared. There's no reason to square anything. So again, if that A was just a simple change in V, if that's all that meant was change in velocity, then yeah, this is Newton's equation. But that's not what he's saying. That's not what that A represents.
The product of the object's mass m and acceleration a. For this equation to be true, the units on both sides of the equation must be equal. So the units of force must be equal to the units on the right-hand side of the equation. We can find that. Square brackets follow the normal.
Yes, and the simple solution is just to say mv is momentum. Momentum is force. That's what Newton basically said, is the two are equivalent. So a force essentially is a momentum that you can take or not take. And likewise, motion is a force you hold, you have, and like money, you can give it away. So you can have $10 of force, and you can give half of it away, or 3/4 of it away, any number of it away, any number of percentage of it away.
Distributive property of multiplication, and can be applied to m and a individually. We know that the base unit for mass is the kilogram, and the base unit for acceleration is meters per second squared.
So it isn't. So that doesn't make any sense. An acceleration is just a change in velocity, and it's, again, Newton's formula was 9.8 meters per 1 second, not per seconds and not per second squared. It's 9.8 meters per 1 unit of time, and that's exactly what happens when something free falls. It gains 9.8 meters of velocity per the seconds it's in the force, that it's being pushed by the force. All right, clearly no seconds squared. So again, it's just so wrong to put and say this is what Newton said. Newton didn't say this. This isn't his physics. This is Leibnizian physics. Newton's worst enemy. That's whose physics you're teaching. And you're putting Newton's name on it. And you're insulting Newton, in my opinion, because Newton was right and Leibniz was wrong. There isn't any living force. There's just quantity of motion. There's just momentum. The universe runs on momentum. Spaceships navigate based on momentum.
Since this product cannot be reduced further, we know.
So again, it's just wrong. This second squared is not a real thing. You can't square a second anyway. It doesn't have any geometry for squaring. It can't make any rational sense. The only way it can mean anything is if there's a direct proportion to the time and some sort of geometric quantity, something that can be squared. Okay? And there is in free fall. But it's the time that's in control, not the distance. So yeah, it's 1, 3, 5, 7. And all of that ends up being, you add the 1 and the 3, you get 4, square root of 2. That's how much time it takes to do the 1 and 3. Okay, so you're just squaring the time to get the distance. But the time isn't a squared unit. The relevant fact is that the time is controlling the distance. And you don't you don't deal with the fact that the distance keeps increasing because the velocity is increasing by saying somehow the time is the squareable function.
Know that the base units of force then are the kilogram meter per second squared.
Which is just all wrong. Okay, it's just wrong. Wrong, wrong, wrong. There's no such thing as the squared second. It's just wrong. It's not Newton's physics. And you shouldn't do this. I mean, you shouldn't be teaching deceptively. And it's an insult to the true history. If you did the research, you'd see Newton didn't say that. Newton didn't believe that it was 1/2 mv squared. And he didn't believe in what Leibniz believed, which was just mv squared. He didn't believe it. He opposed it. So you're saying his second law was a law he opposed. And, that should bother you. If my accusation is legitimate, it should bother you that somebody's accusing you of lying about Newton or deceiving people regarding who Isaac Newton was and what Isaac Newton's mechanics was. You're not teaching Isaac Newton's mechanics. You're teaching someone else's.
Forces are common quantities in physics, and the base unit of kilogram meter per second squared doesn't exactly roll off the tongue.
Yeah, well, whether it rolls off the tongue, it doesn't make any sense. Per second is why you're doing it. It's because you have some notion that an acceleration is per second when, well, no, it's only in gravity that really works. There's no other natural phenomenon that's per second. And clearly it's a rate. And it's just telling you it's this quantity, and you can have a certain number of seconds, but there's no reason to say seconds squared. You can fall in gravity a certain amount of time. 4 seconds, 5 seconds, 6 seconds. Why would it be seconds squared when it might only be 6 seconds? I shouldn't square the 6. That's not going to give me the right answer. All right, so enough of that video. We'll move on to the other one. Alright, should be back. Hopefully this will work. Anyway, so, yeah, he's, I'm going to get off on the wrong foot because, I can't help but notice things and I don't like them, and I say I don't like them. So anyway, he's trying to make the video entertaining, so he has this Super Mario crap in there. And then he's, he titles the video Mind-Blowing Kinematics. It's not really. I mean, it's a little clickbaity, this whole thing. Anyway, unveiling the secrets of one-dimensional motion. And then the secret is you analyze it with 2 dimensions, which doesn't make much sense. Talking about one-dimensional motion analyzed in 2 dimensions. Come on. Sort of cheating, but anyway.
Have to be one-dimensional. Just the direction of motion must be.
Sorry, I thought I was done with this stuff.
Here we go! Okay, glad we cleared that up. So, in some of the examples we'll soon cover, this can include anything from a rocket ship launching into the air, a car moving down the street, or a train moving along a track.
All right, so let's use all of those examples. Okay, so look, there's really no point. I don't think, there's this huge problem in physics in the sense that it was never resolved in the past between this momentum stuff and this kinetic energy stuff, and they are not compatible in any way. Anytime I change the mass of objects that are going to exchange their energy, I end up with huge problems where I'm going to end up making free momentum, or I'm going to lose, megatons of kinetic energy. A simple example, right? The bullet in the gun. So theoretically, the gun only recoils with 2 joules. The bullet leaves with 2,000 joules. By that argument, if I was in a war against a bunch of gun recoils coming at me, I could stop all of the gun recoils, 1,000 gun recoils. I could stop them with 1 bullet. 1 bullet could stop all of those guns from recoiling towards me. Does it make any sense? No. Is that the truth? No. Clearly, 1,000 atoms going, 1 mile an hour is the same amount of energy and force as, 1 atom going. 1 atom going 1,000 is the same as 1,000 going 1 mile an hour. I mean, come on. All right, let me get him to the straight line. I like the straight line part, so I'll use that as the first gravity argument.
More on that later, but for now, let's cover some basics. Let's consider 2 points in space, and label them point A and point B. Now, if you were to travel down a path connecting these 2 points, the length of that path is referred to as the distance.
So he's going to get into these distinctions between speed and velocity, like there should be some sort of distinction, which there is not. And this idea that there's a distance and a displacement, when no, there's a straight line and there's obviously a crooked line. So you can play all the games you want, but that's all there are, is, real circumstances. So I'll just go through some of the many arguments I have gone over hundreds of times for which I haven't gotten any rational reply. And, just continue to point out how Their physics doesn't make any sense, and it overtly violates Newton's second law and overtly violates Newton's third law. It doesn't have any respect for them at all. Just a fact. All right, what do I need? I need to get rid of this. All right, so let's use the straight line and explain gravity. It's a rate, okay? And Leonard Susskind, as I pointed out, kind of describes it as just a flow of a fluid in terms of getting the idea that all there really is a differential. And there's a differential at different points in space, and that you could have a point A and a point B, and you wanted to traverse that point. It would be just like analogizing it to a stream. You could just say there is an average amount of gravity, that an average amount of differential in the force that goes through this area. Now, yes, it might be a little less here, a little more here, a little more here, a little less here. So, but it comes out to an average. You could just say it's 9.8 meters per second. You could say per, okay, 1 second. It's 1 second. 1, okay, not seconds. It's 9.8 meters per 1 second of pressure being applied to an object anywhere, let's say, on this line. Let's just say the average. Okay. Okay. And so you're going to traverse the line. What's going to decide? Okay. The distance or the time. So I reduce my velocity slightly. So if I go very fast, I get here and I only have to do a tiny amount of work. So I only take 1 millisecond. So it's at 9.8 meters per second. It's a tiny amount of change. A tiny amount of counter force I have to apply because I went through this field very quickly. So now I only have to do a tiny bit of work. So if it was a stream and I plow across it really, really fast, I mean super fast, it doesn't have time. Not enough stuff is going to move across this differential to cause me any grief. And so I'm not going to have to apply a bunch of energy to stay on course. But the slower I go, the more my course is going to need to be corrected. The more energy I'm going to have to apply in this direction to keep my course. I'm going to have to fight this amount. And if I, 1 second, 2 second, 3 second, 4 second, the more seconds add up, the more force I have collected, and the more force I must apply to counter it, to equal the force that pushed me this way. So you're just saying whatever amount of force pushes you this way, you have to apply a counter force to stay where you are. And that's just a simple truth. And again, it's a thin ice argument you can make. What's deciding whether you fall through the ice? Okay, it's basically just a distance. What's going to decide whether you fall through this thin ice is just going to be how much time you allowed the force of gravity to push through you into the ground. And the less time you spend over the ice, the less total pressure you'll apply to the surface, because it's a time-dependent force. It's about how much time. So that leads us to the simple point where Leibniz fails and Newton was king. And the simple argument that when an object is falling, okay, what matters? The distance it falls or the amount of time it takes to fall. Okay, and so this is right back to Galileo again. So what's the true circumstance? Okay, the true circumstance is if I drop an object from 4 times the height, all right, it's going to go 9.8 meters in this first unit of time. So let's just call it a second to make things easier. And what's going to happen in this second unit of time, which is only going to be 1 unit of time. 1 second to do this, 1 second to do this. So this tiny amount of distance took 1 second. This huge amount of distance took 1 second. And what do I have when I finish? I have 19.6, indicating that all I gained was 2 units of velocity. I only gained 2 units of acceleration. I didn't gain 4 units of acceleration, just 2. Only 2. No squared amount. And I'm going to wait, it's twice the time. All right, twice the weight. And twice the velocity. Why would I think it's 4 times anything? Twice the time in the stream means I'm going to go twice as far down the stream. And I'm going to hit something with twice the force because I gained twice as much force. and I'm going to have twice the velocity demonstrating it. And, that's the truth of it, that this essentially equals this, and this equals both of those things. It's just a unit of time for which you collected a force. So, Dr. John, do you believe, that 1 pound dropped 4 units of distance is the same force as 4 pounds dropped 1 unit of distance? That's the logic your theorem is based on, is that these things are equivalent. That somehow, in dropping 4 units of distance, even though it's just 2 units of time in the force, that somehow only 2 units of 9.8 per 1 second, you only got 2 units of it. That's Newton's physics. And this is Leibniz's physics, that these two are equivalent, when obviously, no, this is just 2 units of time. It's 2 times 1. It's not the same as 4 times 1. It won't get you the same force. This has 1/2 the energy that this will have on impact. All right, so we'll go to the numerous other examples, and the question: do you believe it? Do you really believe this is how it works? So I'll pause to erase. All right, another example is this idea of a 5 mass going 10 velocity versus a 10 mass going 5 velocity. In terms of, this is an experiment that's repeatedly been done. So I know you know this one, but anyway, I'll just draw it real quick. So you add 5 to a 5 mass going 10. You make a 10 mass going 5. All right, velocity, and you lose 1/2 the kinetic energy is lost. So 1/2 the KE is lost, or you've lost it, disappeared from reality. And you can't really argue that it did any bending, or it made any sparks, or the sound, or it got hot, because all of those things require momentum. You can't conserve 100% of the momentum, and then claim that you did a bunch of work. So that's like saying I can have a bowling ball hit a bowling pin and not lose any momentum to the pin. It can't happen that way. You should be able to agree on that. So the scenario would be, what do you think if a 5 mass hits a 5 mass and they're both going 10, then I'm going to create twice the energy here. All right, this will have twice the energy of a 10 mass going 5. Do you really think that if we could do those experiments, that that's the outcome it's going to be, is that I'm going to get twice the compression of some object that I put here if I do this experiment? And then what happens when I take the 10 mass going 5 and the 5 mass going 10, I crash them into each other? Do you really think, because this has 2x the energy by your theory, that it's going to push the collision, that the collision will move in the direction of this thing that has twice the energy? Or do you think the collision will just happen right here and stay right here? Because they have the same momentum. And it's momentum that makes things happen in the universe, not kinetic energy. Kinetic energy won't move anything. And so we could do it in space, we could do it lots of places, and I could just remake the same argument over and over and over again. So I'll just do the bullet one. That seems pretty clear. All right, zip gun. All right. I don't know why that's not drawing, but whatever. Okay, so I put 2 light bullets in the gun and have the explosion, and I get 2,000 joules going this way. And 2,000 joules going this way. And then I put 2 heavy bullets, 1,000 times heavier, in the same circumstance. So this is basically just saying I put 2 guns inside of each other, or I just have 2 bullets. So I could just draw it as 2 guns, but we'll just say they're just heavy bullets. And I do the same experiment, and I get 2 joules and 2 joules. So somehow the same explosion, if I was using this device to detect how much energy the explosive has, one experiment tells me the explosive has 4 joules of energy. The other experiment tells me it has 4,000 joules. So what do we think the reality is? Which test is more accurate? Which one is telling us the truth? All right, come on. We know it's just momentum. Momentum gets the right answer. Kinetic energy gets the wrong answer. If we did this in space, if we shoot the bullet out one side of the ship and I shoot the recoiling gun out the other side of the ship, so the thing with 2,000 watts of energy is going out one side, and on the other side I'm only sending 2 watts. Does the spaceship turn? And if I convert it in directly into heat, and I'm just saying, look, I'm okay, let's convert it into heat. I'm sending 2 watts one way, I'm sending 2,000 watts the other way. Obviously the spaceship's going to turn. But we know it won't if I do that experiment because the momentums are the same. And momentum moves things in space. Alright, so, which one was I going to do? I forgot. Alright, well, I'll just do the ballistic pendulum and see if I remember the other one. So we have the ballistic pendulum, another one, just tells you the truth. I mean, it's telling you there's something very wrong with your theory. So you have something with 2,000 joules going into a ballistic pendulum. All right, now the momentum, okay, is a number. We'll just say the momentum's 100 just for fun. And the fact is now it goes into this ballistic pendulum. I'm gonna conserve most of that. I'm gonna get like 98% of my momentum is going to be conserved. So the ballistic pendulum will move. Okay, it will convert the bullet's motion. All right, there'll be some displacement, some loss to heat, and basically absorb most of the motion and give it to the big heavy ballistic pendulum, and it will retain most of the momentum, so we'll end up with 98 here, okay, in momentums. But what happens to this? So we conserve 98% of the momentum, but the kinetic energy, we lose 99, according to Professor Lewin, 0.94. Okay, we lose 99.94% of the kinetic energy. And where do we say it goes? Now again, if you say it went to displacement and heat, well, how can I conserve the momentum and make something else move? How can I possibly make something move, go somewhere, and I don't have to use anything's momentum to do it? I can make it happen by having something hit it that has a momentum, and it still has all of its momentum when it's done hitting it. You know, 100% of its momentum, it still has it all. How can it still have all of its momentum and make something else move? That's obviously free energy. That means you have energy going this way and you have energy going that way. You can't have energy going both ways. Come on, it's free energy. Obviously, the theory is wrong. It doesn't work. It's a complete unresolvable paradox. You can't conserve 98% of the momentum and destroy 99% of the kinetic energy. It doesn't make any sense. Oh, okay. Yeah, I'll do the scale one just because this one is one, you know, they've never done it. I mean, I haven't found a single place where physics even talks about doing this simple experiment. So you have a scale, and all you do is, well, your theory says, so let me do what your theory says first, right? Your theory says I have 2 objects, 1 pound each here. I put one of them on the scale. I have now 1 unit of energy, okay? And then I take this second one and I put it on the scale. I do the exact same action, and now I have 4 units of energy. So even though I don't have twice the weight, and I have twice the spring compression, I now have 4 units of energy stored in that spring. Come on, does that make any sense? I do 2 units of work and I get 4 units of energy. That can't be the truth. That's free energy. Come on. All right, so another scale example. All right, I have a scale. This is the one they never show. All right, and I put an object on it. It displaces. Okay, so the scale compresses the spring a certain amount, indicating its weight. Okay, the weight of the mass. So it's connected to the mass proportional. By Hooke's law, the springs work. They do this with regularity. We can depend on them to some extent in terms of how much they'll compress based on how much mass we put on them. And all I do is turn the scale sideways. So I lock it in this position. I lock the scale with the spring, and I put it horizontally. So now I have a compression stored in the spring, okay, with my lock. All right, and now I'm going to see how much velocity it gives the object, because that velocity will be telling me exactly how much energy the object absorbs from gravity, right? I mean, it'll give me a pretty good indication of what my constant momentum is into the ground. I mean, I can feel the fact that I'm constantly pushing into the ground because I can feel the ground constantly pushing back. I mean, I don't feel me move. I feel the ground push me back. All right. And so we know I must be pushing into the ground with some sort of momentum or pressure or weight. And the fact is that my contention is this will be 1 mile per hour. And it doesn't matter what the object is. So I could put an elephant on the scale and then turn it sideways and the elephant will move 1 mile an hour. Put a mouse on the scale, tip it sideways, the mouse moves 1 mile an hour. And the vice versa is true. That all I have to do is swing something into a scale, okay, horizontally, all right, at 1 mile an hour, and I will be able to read its weight without using gravity. 1 mile an hour will tell me its weight. Okay, so an elephant goes in 1 mile an hour, I'll read the elephant's weight. I take a mouse and I read it, I'll read the mouse's weight because it's momentum. I'm just reading the momentum. That's what stores in the spring is momentum. There's no kinetic energy in the spring, there's just momentum in the spring. There's just momentum in the universe. There's no kinetic energy anywhere. It doesn't work. It's paradoxical and nonsensical. So there's a place in his video where he talks about Aristotle and how it took thousands of years for people to say, hey, that doesn't really make sense. You can't do any better than that. And aren't we in the same situation? I mean, it's hundreds of years since Leibniz, 300 years, and you're still believing something for which there's no evidence. I mean, can you honestly tell me that you've seen something where it's taken 4 times the fuel to go twice as fast? So 4 times the fuel going to go twice the velocity. Can you honestly say that you've actually seen something where it's taken 9 times the fuel to go 3 times as fast? Can you say you've honestly seen that happen? 9 times the fuel to go 3 times, spin a motor 3 times faster. Or 16 times the fuel to spin a motor 4 times faster. Have you ever seen anything like that ever? Have you seen any experiment demonstrating that to be true? I'm just saying. Can you say that you ever have seen any experimental evidence that that is true? Have you ever seen any experimental evidence that 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet? Do you have any experimental evidence? All right, so physicist Michael, this is the experiment he's supposed to be doing someday, with a large partial Newton's cradle. Okay, so a nice big one, and a semi-high-speed camera. I mean, 970 frames a second. Should be able to prove this. So anyway, this is what physics says. So again, you've seen this. You have some sort of evidence that this really does happen. So I have a simple Newton's cradle, and I'm going to bang 1 ball. Okay, and let's just say I have 3 other balls here, and I swing this one in. Okay, and obviously only 1 comes out, right? Okay, so all I get is 100 in, and I get 100 out. But if I glue these 3 together, okay, their physics says, okay, that now I have a 3 mass, I have a 1 mass here, okay, and now I put in the same 100 momentums, same energy in, okay, and now this is going to fly out with 150 momentum, okay. So it's going to have 2/3 the velocity, and it's obviously 3 times the mass, so it ends up being this big, huge increase in momentum going this way. And this one will bounce back with 50. So half the energy is coming back this way. All right, and I'm going to get more than half going this way. So I'm going to take 100 momentums and increase them into 150. And I don't have to do anything. It's just magic. I get this extra 150. And that's a classic experiment that physics says happens all the time. They use carts, they use air tracks, they use all kinds of stuff, and they basically say, yes, you can put 100 momentums in, and you can get 150 momentums out. And if you take it to 4 or 5, you might even get 200 momentums out. So if you make it barely move, heavy enough to barely move, you'll get twice the momentum will go into the object. That's what your physics says. Now, the implications of doing it with a Newton's cradle is, well, then you have to deal with what the consequence of that is, which is now you have 150, right, is going to be going in. It's coming back now. Okay, the 3 mass is going to come back in, and the 1 mass, they're going the same speed. I mean, they're going, yeah, they're going the same velocity. Okay, so it just happens they end up going the same velocity. So this is going to be coming in. They're going to hit again right here in the middle. And so this has a 50 momentum coming in this way. So now you have essentially a car crash with 150 and 50. And after the car crash, the only thing that's going to pop out is the 3 mass is going to be dead still. And all I'm going to do is get back the 100 I started with here. That's all I'm going to get out. So I'm going to have a car crash head on. Okay. 200 momentum total in the motion, and only 100 is going to pop out. I'm going to destroy half the momentum, and there's going to be no explanation for where it is. Where did it go? What happened to it? And then it's going to do the same thing all over again. It's going to recreate the 150. It's going to double the momentum, and then it's going to lose half the momentum, and it's going to double the momentum, and it's going to lose half the momentum. Do you really think that happens? You think that's real physics? Because that's what the kinetic energy formula says. That's what the physics book says. I'm simply countering it. Till I see it, I ain't going to believe it. And can you show me that happening? Do you have any real evidence that it actually happens? Any good evidence? Valid question. Alright, so I guess we'll sum up, keep this semi-brief. Anyway, so the rest of his video, he talks about some trail in California and does his little displacement argument versus distance argument and, calculus. And really, calculus is still a way of averaging. It's never going to give you a specific perfect velocity at any location. It's always going to be some average over the units of time you can actually detect. So, they can pretend there's something called an instantaneous velocity, but there really isn't, because we don't have an instantaneous watch. So we can't do, 1/2 instantaneous or something. We can't measure a half of an instantaneous and see how far something or how fast something was going in a 1/2 of an instantaneous. So anyway, it's all kind of for naught. And then the rest of it, he does the same thing, basically talking about trains and the vectors and the slope. And all of that is fine, but it's all a generalization. And you can do it the easy way or you can do it the hard way. It is a simple enough argument. I mean, you can just plot it on a piece of paper. You can just plot the amount of time the train is stopped and then take the average velocity for the distance that remains, blah, 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 blah. And you can do it lots of different ways to do the geometry. And yes, the math can make it shorter, but it doesn't necessarily make it better. I mean, you can count the beans in a jar, okay, by calculating the volume of the jar and how much displacement there is per bean on average. And or you can just count the damn beans, And my argument is it doesn't matter if you're getting wrong answers. And you're going to get wrong answers with velocities if you think, okay, what matters in terms of a force or a application of an acceleration, if you think something other than time is the only thing that matters. How long are you pushing something matters. Distance is an illusion, okay? It's illusionary. I guess I should do that one argument against the distance argument. It's just such an easy illustration of how easily fooled people are. Again, the thin ice should be enough of an argument, just pointing out how obviously it's about how long you stand on top of the ice will decide whether you crash through it or not. And the less time you spend on top of the ice, the less force you'll collect, and the less force you'll put into the ground, and the less the ice will be likely to break. So the rolling velocity argument, because it really just shows how this is Galileo. Galileo pointed out that you can do this slope thing, okay, this idea of making a a ramp and rolling things to slow everything down so you can see what happens. I mean, that's how he figured out the 1, 3, 5, 7 thing, is he slowed down gravity by forcing gravity to act on something rolling on a slope. The simple truth is you can have a zero slope and the same exact law applies. Okay, it's still Galilean. All right, and the simple truth is that if I have a 1 velocity and a 2 velocity, same mass object, the 1 velocity runs out of energy here, and the 2 velocity goes 4 times the distance, maybe more, frankly. Most of the experiments indicate you can get even more out of it. And the simple truth is this 4 times the distance doesn't mean 4 times the work. This is not 4x the okay work. All right. The fact is the ground will only get twice as hot. So whatever this is doing, right? This slow movement means you've got a lot of contact, means you're jiggling the ground a lot. So the ground's getting jiggled. You're a lot of weight. You're putting a lot of pressure. If I put a scale here and measured this total weight, okay, it's going to equal exactly this total weight. Because the trick is, just like in the Galilean falling thing, here is where I go half the speed. Just like Galileo, you drop something 4 times the distance. Okay, 4 times the distance it's going to fall. It's going half the speed right here, way up here. This is half the speed, right here, half the speed. So the other 3 units of distance don't mean anything in the sense that this is half the speed here. Half the speed isn't in the middle. Half the speed is way up here. All right, the same thing happens here. You're going half your speed here. This friction will equal this friction. This experiment, essentially, from right here, you're going 1 velocity. So this experiment here will essentially equal this experiment here. And the fact is that's 1 unit of time. And this is going to be 1 unit of time. And this is going to be 1 unit of time. That's all it is, 1 unit of time. So you traveled this whole distance, and because you were putting very little pressure in, the pressure you applied to this whole distance will be exactly the same as the pressure you applied to this small distance. Over those distances, you applied the same pressure. And by applying pressure, it's the same thing as saying you gave away your momentum. So you start off with a certain momentum, $100. The fact is, in this example, you gave away $50 here in this whole section, and then you gave away the other 50 here in this little section, because you had the hands could get to you. Okay, you were going too fast for the hands to grab it here, and you were going slow enough where the hands could get to your dollars and take your dollar bills. But that's all it is. You start with 100, you lose 50% of it here, you lose the other 50% here. It's only twice the work, not 4 times the work. There's only twice the heat in the ground. Have they ever done the experiment? Have they ever really tested it? Have they done anything? No. Physics couldn't care less about really examining this elemental physics. And all of the accelerator physics is based on 1/2 mv squared. So if it's wrong, it means the weight of an electron is wrong. Which makes sense because, right, they'll tell you the electrons and protons, if I add up all their weight, it's 1% of the weight of a person. Well, that's maybe because you weighed them wrong, but you're using this wrong equation to weigh them. And obviously all the other accelerator stuff, all the neutrinos and patinos and xenos, all of that crap is all made out of the fact that they have energy left over in systems because they keep thinking when I go from a big thing, like an atomic nucleus moving, and I convert it into the little bits moving, all of a sudden I make huge amounts of extra energy because the little bits have a higher velocity. And the velocities are all squared. And that's a huge disaster. All right. So I think that's enough of a video to point out all the paradoxes and nonsense. I mean, there are more arguments I can make. I mean, we go back to Deschardelet dropping round things and denting clay with a round object, not penetrating the clay, just denting it. And the fact is that, yeah, I can dent the thing with twice the velocity and I'll get 4 times the displacement. Well, that's because it's a round object, meaning the thing that dents less far is hitting the bottom surface more, and the thing that goes deeper is pushing sideways more. So the two things aren't applying the energy in the same way and aren't doing the same amount of work. The deeper it goes, the less work it has to do to go deeper. simple fact. No, and again, going back to the simple argument, 1 pound dropped 4 feet is not the same energy as 4 pounds dropped 1 foot. They don't weigh the same. They won't displace a scale the same amount. It's just wrong. All right. That's probably enough. So I'd like there to be engagement. He has a website, so I'll go take a quick look at that. So he offers tutoring, no doubt at a price. Okay, so I just have to find out if the price is within reason, and I will do that. So I can contact him through this form. So he doesn't give any prices online, but you can get these different amounts of help, and I guess you have to pay more for how advanced the help is. And all of that. Oh, look at it. He has a Newton's cradle in here. Okay, that's interesting. Yeah, in the context of one of the arguments made, it's interesting. Because their physics isn't Newton's physics. It's just a simple fact that they're Leibnizians. They should call themselves Leibnizians. They shouldn't say that they have any respect for Newton, because they don't have any respect for him. Clearly, you're not showing respect to Isaac Newton by saying he said things he didn't say. And he never said per second. He never said second squared. And he certainly didn't say twice the force, 4 times the energy. Never said 4 times the velocity, or twice the velocity, 4 times the energy, or force. He certainly didn't say that. He said exactly the opposite, in the sense that he made it clear. 2 units of force, 2 units of velocity. All right. So I think that's enough of a video. We'll see what we get. I can just do my part here, which is point out that physicists are, frankly, belligerently kind of ignorant and ill-informed, and they will not be told they're wrong. They will not allow it to be explained to them, and they will not accept what are obvious truths, that none of this has been cleaned up. Shall I even ask you the Eddington problem, right? I mean, Eddington did an experiment in 1919 with a solar eclipse from Earth. In his journal, he conceded that his data was terrible. He got 10% of the data quality. He was hoping for 10,000 stars per glass slide. He got 1,000. Terrible. And then he even says in the journal, I wouldn't stake my life on these results because, frankly, everything went wrong. Okay, the slides were broken, they were ruined, lots of shit happened. It just was a disaster, frankly. And that was a New York Times headline, Einstein proven right. Never repeated from Earth beyond the margin of error, and never attempted from space with 400 times, not 4, not 40 times, 400 times better seeing. You can actually, because of that 400 times better seeing, you can overcome the 100 times less gravity you have on the surface of Jupiter. So you could actually do the experiment looking at Jupiter, okay, and still have 300 times better viewing. And you don't have any of the corona of the sun problem. You don't have to worry about being outside the corona of the sun. There's no corona of Jupiter to worry about. You think that's good science. You think that's physics that should be respected and that people should trust you. When that's the depth of your investigation, that's how much physics couldn't care less about shoring up any of these elemental arguments they make. They say a photon is twice as bent by gravity, but the fact is, the only imaging experiment, they won't confirm it actually works. And the only experiments they do are scatter experiments, where you can't tell the difference between hitting a particle and being moved by gravity. Moving a whole image proves gravity done it. Okay, scattering an image doesn't prove gravity did it. All right, I don't need to. I mean, there's so much to this, and they've ignored all of it. And they just keep saying it's not my job. Each one of these physicists keep saying it's not my job, it's not my job, it's not my job, it's not my job, it's not my job. Whose job is it? Who's making this the truth? the people making it the truth are the teachers. Shouldn't they be the ones accountable? I think so. All right, anyway, till the next time and such, so forth and whatnot. No offense meant. I'm just, obviously, I disagree with what you're doing, and I disagree with what you're saying, and I don't know how to make my arguments any more politely and still make them. So this is all the best I can do.